Okay, so the topic today is energy. Um, so we'll introduce energy as simply as possible, and then we'll look at how the entire, you know, I guess universe can be thought of in terms of the relationships between energy transformations. So let's start with, the simplest thing we can talk about, and that is the definition of energy itself. Let's get a nice color for energy. Blue is nice. So up until now, we've essentially, I guess, basically talked about various forces, how they, how they interact with each other. We've talked about Newton's laws, okay? And up until a certain point historically, people really only sort of thought about the world as, I guess, a collection of various different forces that pushed and pulled on each other and interacted. I mean, magnets exert a force on each other, electric charge exerts a force on each other, the Earth exerts a force on you and I. But around the time of the Industrial Revolution, it was starting to be noticed that, there's got to be some relationship between things like force and heat, for instance, right? So something like a steam engine works by creating pressurized steam, which then moves pistons. So we're able to get somehow from heat the ability to make a force. Okay, that doesn't really fit into, say, like Newton's set of motion laws. There's no provision for something like heat in there. So you have to start thinking about the world in a little bit of a more, I guess, sophisticated way. It's not necessarily more sophisticated, but it's a different way. How do you relate something like heat to something like motion? And something like motion to being able to, like, roll up a hill, for instance, or, say take a battery and use that to make a light bulb bright, and then maybe, again, use the same battery to lift a small weight up, using a motor and a pulley. How does all of this fit together, and how is it all related? Okay, and the concept behind all of this, the pervading sort of background thing, I guess, that's going on, is this concept of energy. So we start with the definition of what energy is, and I guess maybe the way to sort of get to this is let's review what a force is. Well, a force is a push or a pull. And we sort of learned that there's really only four things that can provide a force. Okay, and the ones that we generally experience on the scale we're at are the electromagnetic push and pull and the gravitational push and pull. Okay, so even when we're, like, pulling on a rope, it's the electrostatic forces within the rope that allow us to provide a tension through it. It's the attraction between, say, the molecules that make up that rope, or the fibers within the rope, which are made of molecules, and then at its core, that's electromagnetic, right? When we have an object suspended from a rope, there's a balance between electromagnetic and gravitational, and so on. We spent time studying all of this. Okay, so force is a push or a pull. Um, um, you know what? And let's just add something here. Let's put energy and work, because they are connected. Energy and work. So actually, before I define energy, I'm going to define work. Okay. So force is a push or a pull. Work work is the providing a force across some length or distance. Okay. So if I just push on the wall, I get it. With Newton's laws, I'm pushing on the wall's staying still, it's pushing back on me. The net force in that scenario is zero. We have an understanding of that. Okay? If I take an object and I provide a force on it, but now the object moves, how do I get the ability to provide that force to make that object move? Okay? How do I do that? What's that? It's magic. I guess at a certain level it is magic. But the definition in physics is that work is the provision of a force, and that force acts over a distance. Okay? So work is force times distance. And that's it. Okay? So far. That's it so far. So work is the providing of force over a distance. So we might have some questions. Um, let's first figure out what units we're talking about. Okay? So force, well, that's measured in newtons, and distance, that's measured in meters. So one unit of work is the Newton meter. Okay? So work is measured in Newton meters. Okay. However, we don't often talk about Newton meters. We actually talk about the unit of work. Does anyone know what the unit of work is? It's the joule. Good. Someone said in the room, it's the joule. Okay. The unit of work is the joule. So the Newton meter distills down into a unit called the joule. Okay. The joule. I don't actually know the history of why it's called the joule. I'm going to make the assumption that Joule was a scientist that probably lived in the Industrial Revolution type era and worked on these sorts of concepts, I should say. How do we get the ability to provide a force for a distance? Okay, we have to do something, right? So let's do a quick example here. Okay, a block is pushed at a constant velocity for 2 meters across a tabletop. Friction is 4 newtons. How much work is done? How much work is required to do this? So let's draw the picture of what this would look like. So there's a block. Here's a tabletop. Okay. And what we're saying is there's a force of friction equal to 4 newtons. So this thing's moving at a constant velocity. What pushing force is required on this object to make it move? Or to keep it moving, I should say, at a constant velocity. What force must be applied to the block to make it continue at a constant velocity? Well, is it accelerating? If it's not accelerating, what does that tell you about the net force on the object? 0, right, because if there's a net force, there would be an acceleration. So the pushing force then must be equal to the frictional force. So we're applying a force of 4 newtons to this object. And during the time we're applying that, the object is moving along, and it covers 2 meters worth of distance. So just remember here, F net equals 0, okay? Inertia says if there's 0 force on an object, it's going to continue as it is. So there's 0 net force. So essentially, you can think of it more or less that there is inertia right on this object because there's a balance between the pushing force that we are applying, right? So it could be you that's pushing it. Here, let's draw you in here. Here you are. You're pushing on this thing to make it go. There's you pushing. And friction is applying 4 Newton force that way. Okay, these balance off to 0. There's gravity, yes. We don't care about that because it's equaled by the normal force, so those cancel off. So essentially, there's 0 net force here. However, the only way we can keep that 0 net force is if we work on this object. We have to push it. We have to push it for a distance. Does that make sense? So we want to know how much work is required in this scenario, basically to make this move and to overcome the work that friction is doing on the object. We'll talk about that in a second. So the work you do is found as follows. Work equals force you apply times distance. You applied a 4 Newton force over 2 meters. So you did 8 Newton meters or 8 joules worth of work during the pushing of this box. Okay? So a question here got asked, and the question was, how can this object be moving if we're only applying an equal force to friction? And in a way, that's right. If this scenario started off with the box at rest, then only applying 4 newtons brings this to a net force of 0. Okay, a net force of 0 with 0 inertia means the box would just sit still. So we have to assume that this already has a velocity, right? And now we're just matching forces to keep it at said velocity. In order to keep it at said velocity, we have to do work. Okay, does that make sense? There's a parallel here with something we're all sort of familiar with, and that's driving in a car, right? In order to accelerate up to whatever velocity we want to travel at, we got to apply the gas, right? We have to do work to get ourselves up to the speed, and we have to do a lot of it. Once we're up to speed, we only have to do or apply enough force to exactly counterbalance off the resistive forces of the air and the friction of the road and all the bearings and so on, right? So it takes less, if you want, work to keep a car going than it does to get it going in the first place. So it takes a little more work to get this box up to whatever speed it's at than to keep it at the speed it's moving at. Does that make sense? Okay, so that's just to clarify what's going on here. At the end of the day, what we're really interested in is this value. 8 joules of work is done in order to move this box across the screen. Okay? Something you'll also notice, though, is that you're going to have a negative force acting against it. Friction is also working in this scenario. Okay? What is the work done by friction? Well, the work that friction is doing is very similar, but there's one thing that's different. The frictional force is in the opposite direction of motion. So we're going to say we have negative 4 newtons times 2 meters equals negative 8 newton meters, or negative 8 joules. The work of friction is negative 8 joules, and the work of the pusher is 8 joules. And they exactly cancel off. If I stop pushing this object, it's going to stop moving in this scenario, right? It'll maybe move for a little bit while the net force, right, the net 4 Newton force slows it down, okay? The way to look at it, the way to understand it in terms of work is I'm doing work equal to the work that, that friction is doing against me. I'm doing positive work, and friction is doing negative work, okay? So far, so good. Now, the next part of this, the next part of understanding work, and we haven't even got to energy yet, but we'll get there in a minute, okay? Work is only the component in the direction of motion. Oh, I should say a force in here. Okay, a force. In the direction of motion. Or maybe even better than direction should be the word plane. And you'll see what I mean in a second. I'll do an example to help you understand what that means. So a classic example that people often do when they want to talk about work is they say, okay, let's imagine that you have a boat sitting in the water, okay? And let's say this side is the this side is the shore, and this side is a lake. Okay, and this is a boardwalk. And in the lake you have a boat. Okay, and you're pulling the boat by a rope that's angled over here. Like that. Okay? So your pulling force then, in this case, is over in this direction. Okay? And let's say that you're applying a tension to the boat equal to, say, 10 newtons. And let's say this boat moves 2 meters, but in this direction. But you're pulling in that direction. And let's say that the angle between the direction that the boat's moving and the applied force is, what does this look like? Let's say 30 degrees. So we've got a 30-degree angle between where the force is going and where the boat is going. So, although we're applying a large force in this direction, it's only a component of the force that's actually moving the boat along, right? Some of the force is trying to pull the boat into the dock, but it can't, right? There's a boardwalk or a dock here that's preventing it from moving in this direction. So the net result is, yeah, there's pushing and pulling and there's offsetting forces here, but we don't care about them because there's no motion in that direction. There is motion in this direction, so we want to know what component of Ft is actually in the direction of motion in this case, right? So how do we define the component of Ft in the direction of motion? How do we do that? So Ft in the x direction, so it's the adjacent angle. So we would say Ft cosine theta, okay? Ft cosine theta. If theta shrinks to 0, right? What's the cosine of 0? 1. If the force is in the same direction, right, as the motion, then Ft and Ft cos theta are the same thing. Right. I suppose that's a way to look at it, yeah. So essentially, what the point made is that if you're pulling in the direction that the object is moving, all of your force is applied to making the object move along. Imagine if I pulled at 90 degrees, okay? And the boat's moving along. Am I technically doing any work? Am I doing work if I pull at 90 degrees on a boat that's moving in this direction? Technically. What's the cosine of 90? 0. So there's no component of force in the same plane as the direction of motion. Therefore, I'm not doing work by the definition that we have here. Okay? So let's rewrite this, and let's rewrite our work formula to say work is actually going to be d times whatever force I'm applying cos theta. So df cos theta. Generally, you don't see it that way. It's just all combined to look like this. Work is equal to f d cos theta. Okay? Does that make sense? So a note or something that we could take away from this is you can only count work is being done if some component of, I guess, or all force acts in the same plane as motion. Okay? The concept of negative work is often hard, okay, to understand, but you have to remember that negative work is negative in the same way that a force can be negative. It's talking about direction. So a classic example of where you might see negative work would be, say, in the gym. Okay, so let's imagine that you're bench pressing in the gym, just getting super jacked, and what you're doing is you're working on the bar, the bench press. Okay, and let's say you're lifting the bench press up. Okay, in order to lift the bench press up, to push it up, right, you need to apply an upward force. It's equal and opposite to the downward force of gravity. Times, let's say you're lifting it 1 meter or some distance. So the work in this scenario to go from the bottom to the top, right, how would we calculate that? Well, it would be, the work here would be work equals the force of gravity, because we have to apply a force equal and opposite, and assuming we're not accelerating the object, we're just equaling the force of gravity, right? Once it's moving, we just have to apply a force equal to the force of gravity, but in the opposite direction to make it go up. Fg times the distance that we moved the weight. Okay? Does that make sense? Right. So Fg is the force of gravity. And how do we define the force of gravity again? We actually call it weight, right? That's funny because it looks like work. That's okay though. Right. So mg, right? The force of gravity, aka weight, is equal to mg. So we'd actually write this formula: the work done by a weightlifter is equal to the force he's applying, so that's mg, right? Times the distance he lifts the object. Does that make sense? Right. Well, no, that's not true. No, that's not how that works. Okay. What I want to illustrate this. What he has done is he's done negative work, which interestingly still requires energy. Okay. And we haven't introduced energy yet, but we're almost there. We're almost at that point. So just bear with me for a second. On the way up, D is positive, right? Okay. The force is up. The distance the weight moves is up. He's doing positive work. However, he also has to return it back down again, right? If he's doing reps, he's got to bring the weight back down again. During bringing the weight back down, look what happens to this formula. The force is still up, right? He's still pushing up, equal and opposite to gravity, but now the weight is moving in the opposite direction. D is down, okay? The force applied is identical, but the direction of motion is opposite. So in this case, on the way down, he's doing negative work. So he's still applying a force in the same plane as the motion, so we don't have a problem there, right? Doesn't matter which direction, it's about the plane, right? The force is up, the plane of motion is still the same, still in the y plane here if he's moving it straight up and down. But he's doing negative work as he's lowering it because the force is up, the distance or displacement is down, okay? Probably a better way to write this, actually, is to put a delta in front of there, right? It's a delta, it's the distance he moves it, it's the delta D between his initial and final positions. But I think we get the concept here, okay? So when we get to energy, which will be next class, we'll talk about how it should, theoretically, take just as much energy to let the weight down as it did to push it back up, okay? Go to the gym and try this out. Move a weight up slowly, and instead of just letting it drop down, bring it down slowly. See how that feels. Like, push it up and bring it down slowly. Bringing it down slowly takes work. It's hard to do. Here's a question. Let's say I push on the wall. Let's draw a straight wall. There's a wall. Let's say I push on the wall. Oops. Say I push on the wall. Let's try that again. Here I am. I'm pushing on the wall as hard as I can. I'm angry. I'm pushing. I'm pushing. I'm pushing. That wall ain't moving. Am I doing work? No work done. Does it feel like I'm working? You bet it does, right? Let's say I take a big kettlebell here. And I hold it out at arm's length. Am I doing work in the physics sense? No, I'm applying a force, yes, but there's no motion. No work. Does it feel like I'm working? You bet. That's hard to do, right? It's hard to do, okay? So you got to be careful. Oh yeah, some of it's sweat and exertion, okay? This is a hard thing to do. It's even hard to do this with like a, I don't know, a pencil actually after a while. Okay, holding your arm straight out like that. Um, you have to be careful in your definitions, right? Work in everyday world is different than work in physics. Work in physics has this definition. Okay? Next class, we'll introduce energy, but that is enough for today.